So last time we started to understand what happens when you put an insulator in an electric field. We learned that all insulators are dielectrics because all matter, even though it's neutral and insulating, is made up of bound charges. And when you turn on an electric field, what happens to the bound charges in an individual molecule in the matter is that the electric field separates the charges inside the molecule by a little bit, making one end of the molecule a little positive, the other end a little negative. Boom, every molecule is a dipole. Now, in some materials, the molecules were dipoles from the start before you turned on the electric field. But in any material, after you turn on the electric field itself makes every molecule into a little dipole, even if it wasn't one before. So whether the dipoles were there originally or they were just created, now you have a lot of dipoles. Those dipoles feel a torque. They line up. And so what happens inside any insulator, inside any dielectric, is that when you turn on an electric field, you end up with a configuration of dipoles like that I've shown here. Now, the question that we're going to ask then is what happens if I take a slab of dielectric, maybe a slab of glass or a slab of water, and I put it inside a capacitor, as we have here. So here I have a standard capacitor with positive charges on the top plate up here, negative charges on the bottom plate down here, making an electric field shown in orange pointing from the top plate to the bottom plate. But now I've slid into here a slab of dielectric. And that dielectric is now in an electric field, the electric field in orange, which is made by the capacitor. So inside that dielectric, this is what's happening. I'm applying an electric field. All those little dipoles are aligning. And now we have to ask what the consequences of that are. So every dipole makes an electric field. If we think about this dipole over here, it's making an electric field. Here's the plus side of the dipole. So it makes an electric field that comes around and points back this way, goes in here. Comes around, points back this way, goes in here. This dipole down here makes it an electric field, comes around, points back this way, goes in here. Comes around this way, points back this way, it goes in here. So all these dipoles make electric fields. You take the vector sum of all those electric fields, and all these dipoles, the dipoles which are pointing this way, add up their electric fields all together, and it's going to make an electric field that's pointing back this way, against the direction of the original field. Now, there's another way of thinking about this and reaching exactly the same conclusion. And that is to say, let's do a little regrouping in our minds. Let's look at this region of the dipole, of the dielectric here, and see, oh, these charges cancel. I've got some plus here and some minus here. That cancels. Then I go a little farther over. With this region, plus and minus, that cancels. Go a little over here. This region, plus and minus, that cancels. So all the charge in the interior of the dielectric neutralizes. But then I've got a sheet of negative charge on the left and a sheet of positive charge on the right. So now let's think about what the electric field is that I get from a sheet of negative charge here and a sheet of positive charge there. And look at that. It's an electric field pointing this way. So either way you think of it, what's happening inside the dielectric is first I, from the outside with my capacitor plates, apply an electric field that's pointing this way. That makes lots of dipoles inside, or maybe the dipoles were there already. Either way, I have dipoles. They line up. Once the dipoles line up, the dipoles themselves make an electric field which points back this way, partially canceling the electric field that I originally applied. So if we now go back to the capacitor, that is what is shown in this diagram. I start with some original charge, sigma, here, some original charge, minus sigma here. That makes the orange field that I started with. That orange field polarizes all the molecules inside this dielectric, and that makes a yellow field pointing back the other way, called the induced field. So the induced field points in the opposite direction as the original or vacuum field. The original field is that's the only field that would be there if I had just had vacuum in here, so we can call it the vacuum field. And so what that means is that if I ask what the electric field is in this capacitor now, it's not what I had before. So what I had before, let's say that in the absence of any dielectric in here, so if I just had vacuum in here, I have an electric field E naught. The electric field that I have now is not given by E naught. It's given by the vector sum of E naught plus E induced. So E naught is the orange arrows. They point down. E induced is the yellow arrows. They point up. And the strength of E induced is actually proportional to E naught. So the result is that the magnitude of E is less than the magnitude of E naught because E induced is pointing in the opposite direction to E naught. So this is not the way this is usually written. The much more conventional way of writing this is to say that when I put my dielectric into the capacitor, the electric field is reduced relative to the value it would have in vacuum by some proportionality constant called kappa. So the electric field, instead of being E naught, is reduced by some factor kappa. And kappa is a materials property of the dielectric in question. It'll be different for water than for paper. And when I insert the dielectric into the capacitor, what's happening inside the dielectric, dipoles aligning, they make a new electric field shown in yellow, which partially cancels the original electric field E naught, reducing its magnitude. And so the actual electric field that I get when I put the dielectric in is E naught over this kappa. OK, so how large is kappa? Well, it will depend on which material we're talking about. So by convention, if the material we start with is a vacuum, well, for vacuum, there is no kappa. Kappa is equal to 1.00000000000. In other words, if what I have between the plates of the capacitor is vacuum, then the electric field is just E naught. Now, for air, kappa is very, very close to 1.0. It's 1 point, many zeros, and then some non-zero digits. But water has a kappa, which is in fact 80. So what that means is that if I slide a container of water in between my parallel plates, the electric field will be reduced by a factor of 80. Another way of saying it is that if I have water between the plates of a capacitor, the yellow upward pointing field is 79/80ths as big as the orange downward pointing field, which is the one I would have had in vacuum. So I almost completely cancel the orange field with my yellow field. I cancel 79 out of 80 of it, and the result is that I reduce the magnetic field by a factor of 80. So water is an extremely good dielectric, and the reason for that is that in water there are permanent dipoles that are there even before I turn on the electric field. What about paper, another material that I mentioned? So if I slide a stack of paper in there, how good a dielectric is paper? Well, paper has a kappa of 3.7. So sliding a stack of paper in there will reduce the electric field in the capacitor by a factor of 3.7. One more example, what about Pyrex glass, like the glass on which I am writing? If I took a slab of this glass right here and slid it into a capacitor, how much would it reduce the field by? Well, its kappa is around 5.6. So what does kappa do? Well, if you take a capacitor and slide a slab of dielectric into it, keeping the charge on the plates the same as it was before, the electric field is reduced by a factor of kappa. Now I'm going to show you 4 more ways of seeing the same physics. So first of all, let me remind you that for parallel plate capacitors in vacuum, E naught can be related to the charge density on the 2 plates. I've got a charge density sigma here, charge density minus sigma there, and we learned previously that for parallel plate capacitors, E naught, the electric field, is sigma over epsilon naught, this constant that we initially introduced via Coulomb's law. So if E naught is sigma over epsilon naught, well, that means that E, what's E? Well, E is sigma over kappa epsilon naught. And what you see is that putting a dielectric inside the capacitor is like taking epsilon naught and replacing it by kappa times epsilon naught. And kappa times epsilon naught is often given a name. It is called epsilon. Epsilon is referred to as the dielectric constant. So the dielectric constant of water is 80 times epsilon naught. And epsilon naught is often given a name. Epsilon naught is called the dielectric constant of the vacuum. So the dielectric constant of water, epsilon for water, is 80 times epsilon naught. The dielectric constant of paper is 3 point something times epsilon naught. For Pyrex glass, 5 point something times epsilon naught. So the second way of thinking about what kappa does is that the kappa of a dielectric tells you how much larger epsilon is as compared to epsilon naught. So that's our second way of thinking about kappa. Now let's do the third. So for the third way, we go back to the first equation that I wrote here, where I first introduced kappa. And I'm going to multiply on both sides by d, just because I feel like it. What's d? D is the distance between the two plates. D is this distance here. So because I feel like it, I'm going to multiply on both sides by d. So d times the electric field E is equal to d times the electric field E naught divided by kappa. And then I'm going to take absolute values. Why did I do that? I did that because d times the absolute value of the electric field, that's nothing more, nothing less than the voltage V across the capacitor. And d times the absolute value of E naught, that's nothing more, nothing less than the voltage that you would have had across the capacitor in vacuum. And here I have kappa. So the third way of thinking about what kappa does is to say that if I slide a dielectric into this capacitor, keeping the charge on the two plates fixed, what happens to the voltage across the capacitor? Well, it's reduced by a factor of kappa. And this leads us directly to the fourth way. Fourth way is to think about the capacitance. So what does kappa do to the capacitance? Well, let's remember what the capacitance is. The capacitance of a capacitor C is Q over V. And we're keeping the charge fixed. And when we keep the charge fixed, what happens to the voltage? The voltage goes down by a factor of kappa. So Q over V, this is going to be Q over V naught, and then there's a kappa up here. So C is equal to kappa times C naught. So what does a dielectric do in a capacitor? It increases the capacitance. It increases the capacity by a factor of kappa. And that's our fourth way of looking at this. The fifth way, maybe I shouldn't call it a separate way, the fifth way follows directly from what we've done. What does it mean that the capacity of a capacitor has gone up by kappa? Well, what that means is, suppose that instead of keeping the charge fixed, which is what we've been doing up to this point, suppose that I connect my capacitor to a battery, not shown in the diagram, and that battery is going to maintain a voltage V no matter what I do. It's going to keep a voltage V across this capacitor. And now I slide my dielectric in. Because the capacitance is larger by a factor of kappa, that means that when I slide my dielectric in, the capacitance goes up by a factor of kappa. That means that the charge on the plates is going to go up by a factor of kappa. Which is to say that since I've increased the capacitance, if I hold the voltage fixed, that means I have to increase the charge on the plates by a factor of kappa. So you can think of this one of two ways. You can either think of it the way we started, that when I slide the plate of dielectric in, I'm going to keep the charge fixed. That means the voltage goes down. Or I can slide the plate in, keeping the voltage fixed. That means the charge goes up. Either one of these is equivalent to saying that the capacitance is proportional to the original capacitance times kappa. It goes up when I slide the dielectric in. And this is also equivalent to saying that if I hold the charge fixed, the electric field goes down. And all of this, all of these different expressions can all be summarized by the single, in some ways, easiest mnemonic way of remembering what a capacitor does. The easiest way of remembering all of this is, and you can track it through, is that the introduction of the dielectric increases epsilon naught to epsilon, where epsilon is kappa times epsilon naught. So sliding a dielectric in increases epsilon naught by a factor of kappa. It increases the capacitance by a factor of kappa. That means if I hold the charge fixed, the voltage drops by a factor of kappa and the electric field drops by a factor of kappa. But if I hold the voltage fixed, the charge will rise by a factor of kappa. All summarized in this simple way of remembering what I just described.